next speaker is Moran Bercovici. He's an associate professor of mechanical engineering and biomedical engineering by courtesy, excuse me, at the Israel Institute of Technology, also known as the Technion. He's interested in understanding basic fluid mechanisms. He often applies fluid mechanics to solve complex problems, which is something I really appreciate about his work. He holds a PhD in aeronautics and astronautics from a small school in California, Stanford University. He also worked in the med school at Stanford as a postdoc. Among other awards, he's won the Krill Prize by the Wolf Foundation and also the Blavatnik Award for Young Scientists in Israel. So he's going to be talking to us about making lenses using surface tension.
Great. Thanks a lot for the introduction, Juan, and thanks, Flo, for having me. So yeah, diving right to it, I'm going to show you how we leverage fluids to create useful, hopefully useful optics. Before I start, since I know I'm going to run out of time, I first want to give credit to the people who are really behind this, starting with Valery Frumkin, who was a postdoc in my lab, who really started all of this. The credit for the nice solutions and creative ideas all goes to him. And continuing this work in my lab now, Valery is now at MIT, are Mor El-Gharisi and Omer Luria, who have taken this to new heights, and you see their results as well. I'm going to show some things that we've already published in Flow, some things that have just recently been accepted, and some unpublished work and future work. So I don't think that optical components really need an introduction. They're everywhere. Everyone knows what they are, from eyewear, glasses, to cameras, medical devices, defense, astronomy. We have optical components everywhere. And how are they currently being fabricated, being created? Well, pretty much the same way that they've been created 300 years ago. So the process is a mechanical process that involves the first step of grinding, so taking a piece of material and giving it its shape, and a second step of polishing, which is really getting to the required surface quality for the optical application. Now, modern mechanics looks much better and is automated, etc. But the principle remains the same. This requires a factory, heavy, specialized, very expensive equipment in order to do that, which makes it really not very feasible for rapid prototyping, and also not very feasible for operation in low resource settings. And low resource settings can be developing countries, but can also be the space environment, which is also very constrained on resources. I said rapid prototyping, and the first thing that comes to mind typically is 3D printing. And the question is, why not use 3D printing to make optics? Well, 3D printing is amazing and it changed the world, and you can print almost anything. Well, almost anything. You cannot print optical components. And the main reason for that is that even the best 3D printers cannot reach the surface quality, the typically nanometric surface quality that is required for optics. One more limitation for 3D printing, an inherent one, is that the printing time is proportional to the volume. So if you want to create a very large component, or if you want to create many small components, you start getting to unreasonable times. So we're in fluids. Our inspiration comes from droplets. This is a beautiful picture taken by Valery of a water droplet in this case. And droplets, at least when they're small enough, they're spherical. And a sphere is a really good start for optics. You can also create droplets from various liquids with different optical properties. And perhaps most importantly is that due to surface tension, their interface or outer surface is extremely smooth. However, in order to take droplets and create useful optical components on relevant scales of, let's say, centimeters or more, you have to fight a serious problem, which is as you increase in scale, a very annoying force starts kicking in, which is gravity, right? And so as you increase the size of your droplet, it is no longer spherical. And for large enough droplet, it actually becomes, right, a puddle or a pancake. And that's no longer a very useful shape for optics. This is governed by the capillary length, which is the ratio of surface tension to body forces. And the typical number for fluids, liquids at room temperature, it's about 2 millimeters. So up to 2 millimeters, nice and spherical. Beyond that, it's not very, very useful. And so the way we solve this is by getting rid of gravity. And of course, we can't really get rid of gravity, but we can try to counteract it with an equal and opposite force, and we use buoyancy. So the setup is simply an aquarium, which we fill with what we term an immersion liquid. It's another liquid that is immiscible with the lens liquid that we inject in. And importantly, it has a density that is equal or almost equal, I'll show you some deviations from that, to the density of the lens liquid that we're injecting. So now effectively, we have canceled gravity, we're in neutral buoyancy. And this is what it looks like in the experiment. You're looking now into the aquarium. There is immersion liquid everywhere. Inside the aquarium, we place this frame. It's just a circular plastic frame you see here in the middle. And into this frame, we're injecting the lens liquid. This is a side view and a bottom view here. You can see that the lens liquid doesn't fall down, doesn't float up because it's exactly neutral buoyancy. It likes the surface of this frame we gave it, and so it attaches to it. And you see as we're retracting out, we got the shape of our, in this case, biconvex lens. And the two surfaces, the upper and lower surfaces, as I'll show you, are essentially spherical caps. Let me bring you a little bit into our model. I won't go into all the details, but I do want to give you the gist of it. Here's again a picture of the liquid lens in the aquarium. What we're trying to solve for is the shape of the top surface and the bottom surface is HD and HB as a function of the lens density and the immersion liquid density. Again, when they're equal to one another, we have a zero difference in density and we get an infinite capillary length, right? So with an infinite capillary length, we can remain spherical at any scale. One more degree of freedom, which you did not see in that video, is illustrated here by this blue region. The whole lens can sit on a cylinder or rigid cylinder, and the blue region depicts the liquid that is inside that cylinder. In that region, we can put a different immersion liquid, or we can put the same immersion liquid, but push more liquid into it. And when we push more liquid into it, we inflate the whole lens. So this way we can deviate from symmetry. So we can control the densities, we can control this enclosed volume, we can control the volume of the lens itself, the liquid lens that we're injecting. And of course, we can control the shape of the frame. Currently, this is just a simple circular frame, but I'm going to show you some variations on that later on. So these are our degrees of freedom. Since we're looking for a steady state solution, we can take an energy approach, right? The free energy of the system, try to minimize it. So here it is. Here's the functional, the first two terms. These basically represent the interfacial energy. It costs you energy to create a surface. The term here in the middle, this is essentially potential energy. You can see that when it's exactly neutral buoyancy, this term completely disappears. And the last two terms, these represent our constraints. The first constraint is the volume of the lens itself. And the second constraint is if we're using that enclosed volume, we have to respect the volume that we prescribed there. So we take this functional, we look to minimize it, we write the Euler-Lagrange equations, and we end up with these equations for the top and bottom surface. Now, note that if delta rho is 0, so we're true neutral buoyancy, If you take this term and you divide it by r, what you get is exactly the mean curvature of the surface. And what you're getting is that the mean curvature of the surface is constant. So what we're getting is a family of constant mean curvature surfaces. Spheres are constant mean curvature, cylinders are surface mean curvature, but this can really be dictated by the shape of the boundary into which we're injecting it. So here are some results from the analytical model. You're seeing the blue curve is the top surface, the red curve is the bottom surface. We're changing here the enclosed volume and the volume of the lens. And you can see that we deviate from symmetry. We can create these type of meniscus lenses. We can create biconcave lenses, so negative lenses, and so on, just by controlling these two parameters. So up to now, it's what you saw in that video, right? We injected the liquid. It's still a liquid lens, but what we're really looking to get is a physical solid lens in our hand. So we had the aquarium, we had the immersion liquid. We're now injecting the lens liquid, and the last step is if we choose a liquid that can be solidified. So typically these are polymers that can be polymerized, cured, but this method basically works with any liquid that can be solidified. You try to do it with metals, liquid metals. You could try to do it also with water and freeze it, anything that you can solidify. In most cases, we use a polymer. We turn on a UV light, we photopolymerize it. This takes between 2 and 5 minutes. Once it's solidified, you very literally reach in with your hands into the aquarium, you pull out the lens, and these are the type of lenses, optical components that we can create. So very quickly, here is a convex lens. It's about an inch and a half. Here, this is an example again of a double convex lens, just with very extreme curvature, and is difficult to achieve with machining. These are these meniscus lenses that basically most of us have in our eyeglasses. This is a double concave surface. We painted it red just for easier visualization. This is a cylindrical lens. This is the cylindrical lens, by the way, is using a different boundary condition. I'll show you later. And this is a bifocal lens. So we basically created one lens, we cut it in half, and then we use the resulting lens as the frame for the next lens that we inject. This one is a toroidal lens or a saddle lens, which is concave in one direction, convex in the other, again, using different boundary conditions. And this is a two-step process where we first created a negative, a concave lens that you see in the middle that is transparent. And once we solidified it, we casted the second polymer that we dyed in blue for visualization and created a positive lens on top of it. So you can create doublets, triplets, Napoleon cakes like this of any number of lenses, one on top of the other. So are these lenses any good? Here's one characterization for quality of an optical component, which is the surface roughness. We measure roughness using atomic force microscopy, and we achieve repeatedly surface quality of less than 1 nanometer RMS. This covers essentially the entire range of optical applications, from eyeglasses to telescopes to high power lasers. And the important thing is that this is not done in any sort of clean environment. Here's a demonstration. This is Valerie showing some guests in the lab the experiment. This is the water tank. It's all done out in the open. And dust typically tends to float on the surface of the water, of the immersion liquid, and so it doesn't get to the lens. So I showed you we can use the enclosed volume in order to break from symmetry, but another way of breaking from symmetry is by breaking away from neutral buoyancy. So now let's imagine that we increase the density of the immersion liquid just a little bit. So now the lens liquid wants to float up a little bit. We use the same equations I showed you before, except we linearize them, and we linearize them with a small parameter that is the typical height of the optical component divided by its typical diameter or radius. For most optical components, this is a small number, but not for all optical components. Some can deviate from this. When we use this as a small parameter and linearize the equations, we get a pair of Bessel and modified Bessel equations, where these are governed by the bond number, which is essentially a non-dimensional version of the inverse capillary length. But for us, this represents how much we deviate from neutral buoyancy. And so, not surprisingly, with Bessel functions, we get Bessel solutions. And this is what the surfaces look like as we change the bond number. So look at the blue surface, for example. As we increase the bond number, you can see it starting to float up. This is precisely that J0 Bessel function. And the surprising thing is that two physics from two different disciplines, from fluids and optics, meet very nicely here, is that this Bessel function is the first order correction for spherical aberrations in optics. And these surfaces are typically very difficult to create with standard machining because there are multiple axes required in order to machine this. We get it just by changing the density of the immersion liquid. If I let it continue running, you can see some very exaggerated surfaces. Usually the corrections for A-spheres are very mild, something like this. One more very important point is that when we're in neutral buoyancy, as I mentioned, the capillary length goes to infinity. And when the capillary length goes to infinity, scale basically disappears from the solution to the problem. So the solution is scale invariant, meaning we should be able to create lenses of any size. This is the largest one we created in the lab. This is a 200 millimeter telescope lens. This was done using neutral buoyancy, but actually, even when we deviate from neutral buoyancy, when we use the bond number, we are still scale invariant because the bond number is controlled both by the radius and the difference in density. So for a given shape that we're interested in and a given radius, we can tweak the difference in density to achieve that desired bond number. So this is truly scale invariant, and you can go theoretically to any size. One more degree of freedom that I mentioned before is the shape of the frame itself. And this takes us to freeform optics. It's no longer a lens in the sense that it doesn't have a specific focal point, for example. These are generic surfaces that act on an entering wave front. And the desire is to achieve basically any surface. So we go back to the energy equation, except this time we get rid of the assumption of axisymmetry. So we get a version of the Euler-Lagrange equations that depend both on the radius and the azimuth, r and theta here. And we again linearize them, just like before, with the same small parameter, and solve the linearized equation with a boundary condition, which is the height of the frame as a function of the azimuthal coordinate. Okay, that's a definition of our boundary. So when we do this, we can find a solution as a function of a Fourier decomposition of the shape of the frame boundary. And the resulting solution is a sum of basically Bessel, not surprising, Bessel Fourier functions, and these coefficients are found as a function of the Fourier coefficients that define the boundary. This is what the solutions look like. The columns here are the different modes. So these represent different sign values of the boundary. So this is sine theta, sine of 2 theta, sine of 3 theta, etc. And the diagonals here represent different bond numbers. Okay, so within a given bond number, we can superpose the different modes to obtain a more general solution. Of course, we cannot superpose different bond numbers, right? Because these are simply created using different densities. But if we have a lens that has two different surfaces, a bottom and a top one, each one can have a different shape, and we can superpose those, and each one can be exposed to a different density, giving a different bond number to each one of those. This is what the process looks like for the freeform lenses. We create the frame using standard 3D printing. The roughness of the 3D print here doesn't really matter because it's just the boundary. This, in this case, is a sine of 4 theta. You can see what it does to a grid. And characterizing it, surface quality, surface roughness is very similar to before, sub-nanometric. And this is a characterization of what's called regularity. This is how close is the shape that we obtained to the shape that we actually wanted. I have to emphasize that this is all still handmade. So these are pipetted volumes into the lens, and still we get an RMS over a lens that is about 2 centimeters of 700 nanometers. So a little over a wavelength in the accuracy of the shapes. We hope that this can be even further improved when we go to automation. I want to finish with just a couple of slides of where we want to take it from here. So the key here is really to get rid of gravity, right? And so we got rid of gravity with neutral buoyancy in the lab. One more way of getting rid of gravity is going to space. Of course, you don't really get rid of gravity there as well, but if you go into orbit, then the centrifugal force can balance the gravity of the Earth. We can theoretically do the same thing there, and we don't even have to solidify the lenses. They can remain in their liquid form. And so we teamed up on this with some friends at NASA. We call this FLUT. This is the acronym for Fluidic Telescope Experiment. And this is the fantasy, the vision of creating enormous scale telescopes at the scale of tens or even hundreds of meters by sending a spacecraft that would deploy a frame into which we would inject a liquid that will become the mirror of that telescope. That could be a way of compacting a huge telescope into our existing launchers. To do that, our first station is here. In 2 months, we'll be doing this parabolic flights, where we're going to have short durations of about 20 seconds of microgravity. And we're going to deploy liquid lenses. We're not going to have enough time to polymerize them. So we're going on the flights with no lenses, coming out from the flight with no lenses, but hopefully have a lens in between and characterize it and show that it existed and it's of high quality. If all goes well, then in February, we are sending an experiment to the International Space Station. This is future private astronaut Eitan Stiva. This is the first private mission to the space station run by Axiom. And this is him training on fluidic shaping. He's going to perform it in orbit, and he's actually going to solidify the lenses and bring them back down to Earth, of course, without any immersion liquid, just liquid, lens liquid and air. With that, I want to thank again Flo for inviting me for the seminar. As you saw, we published this work in Flow, and actually we were proud to be the first paper to be published in the journal. It kind of gives away, right, the fact that I'm pretty excited about this journal. And I think it can really become one of the pillars of our fluid mechanics community. Now, for fundamental work, we have good options. But as you saw in our work, the work that I just showed you that I'm very excited about, but we didn't really contribute anything to the basic understanding of fluids. We leveraged the physics of fluids to create what we think is a really application. Currently, there's no real venue for that. When we do things like that, we often go to application journals. So in this case, maybe an optics journal, but that's often too early for something like this. I want our community to be able to see the minimization of energy and the functionals. I want people to think of how it can be expanded within the fluids community. And then, as you saw, the next publication was in Optica, which is a dedicated journal, and it goes into the more specific application. So I think that the mission of Flow covers really nicely this existing gap. With that, thanks for listening. Happy to take any questions, and hopefully, when all this COVID nonsense is over, I can welcome you to Israel, to Haifa and the Technion campus. Thanks very much.
Cool, excellent, thank you. Thank you very much, Moran.